Nature's Number Chapter 5 from Violins to Videos. Would you believe that violin strings is the root of the creation of the television that is being used today? So, all of this started with Greeks' concepts. First, the Greeks knew that violin strings are a potential tool for creating new formulas and inventions. It is because it can be compared to Newton's law of inertia due to the acceleration of the string after it was plucked from its straight line position. Second, Greeks were able to discover that strings can vibrate in many ways and can produce a lot of musical tones when plucked differently, because the higher you pluck a string from its original position, the higher the pitch it makes. Greeks were also able to find out that a string can vibrate at many different frequencies depending on the position of the nodes. Each ends of the string are nodes, and the sound of a single string vary from how far nodes are placed. They were also able to incorporate the sine curve and trigonometry with the standing waves that the strings can make. In sine curves, the distance of the amplitude from peak to peak gets farther depending on the solution that was generated. In 1746, the Frenchman Jean-Léron d'Alembert showed that many vibrations of a violin string are not sinusoidal standing waves. So in response to d'Alembert's work, the prolific Swiss mathematician Leonhard Euler worked out the wave equation for a string in 1748. It was considered to be a partial differential equation because it involves not only rates of change relative to time, but also rates of change relative to space. His formula expresses in mathematical language the idea that the acceleration of each tiny segment of the string is proportional to the tensile forces acting upon that segment, which is a consequence of Newton's law of motion. Euler solved his equation, leading to solutions in which the ends of the string remain fixed. After Euler, there was Bernoulli, who also solved the wave equation, but by a totally different method. According to him, the most general solution can be represented as a superposition of infinitely many sinusoidal standing waves. This apparent disagreement began a century-long controversy and was eventually resolved by declaring both Euler and Bernoulli right. Vibrations of a violin string ceased to be a mystery, and the mathematicians went hunting for bigger game. Objects with more dimensions can also vibrate, and the most obvious musical instrument that employs a two-dimensional vibration is the drum. A drum skin is a surface, not a straight line, so mathematicians turned their attention to drums, starting with Euler in 1759, who again derived a wave equation. This one describing how the displacement of the drum skin in the vertical direction varies over time. Its physical interpretation is that the acceleration of a small piece of the drum skin is proportional to the average tension exerted on it by all nearby parts of the drum skin. The interesting difference of the boundaries of a violin string and drums led to a conclusion that the true role of the boundary becomes apparent only in two or more dimensions. For a drum with a boundary of a closed curve or circle, boundary condition restricts the possible motions of the drum skin. The mathematicians of the 18th century learned to solve the wave equation for the motion of drums of various shapes. But now the wave equation began to move out of the musical domain to establish itself as an absolutely central feature of the mathematical physics. Some of the prominent persons during the 18th century were William Gilbert, who was a physician to Queen Elizabeth I, who described the Earth as a huge magnet. He started the story of electricity and magnetism and observed that electrically charged bodies can attract or repel each other. Second is Benjamin Franklin, who proved in 1752 that lightning is a form of electricity by flying a kite in a thunderstorm. Third is Luigi Galvani, who noticed that electrical sparks caused a dead frog's leg muscles to contract. And last is Alessandro Volta, who invented the first battery. Throughout much of this early development, electricity and magnetism were seen as two quite distinct natural phenomena. After them came Michael Faraday. He has shown that magnetism and electricity were two different aspects of the same thing, electromagnetism. He spent 10 years to prove that an electric current could create a magnetic force, and in 1831 he succeeded. He was asked by King William IV about the use of his scientific parlor tricks, and Faraday politely replied that one day he will tax them. Practical uses soon followed, notably the electric motor and the electrical generator. Faraday also advanced the theory of electromagnetism. He cast his ideas in physical imagery, of which the most important was the idea of a line of force. If you place a magnet under a sheet of paper and sprinkle iron fillings on top, they will line up along well-defined curves. His interpretation of these curves was that the magnetic force did not act at a distance without any intervening medium. Instead, it propagated through space along curved lines, and same went for electrical force. Now we will talk about another prominent person named James Clerk Maxwell and his formulas. He expressed Faraday's ideas about lines of force in terms of mathematical equation. By 1864, he had refined his theory down to a system of four differential equations. First is Gauss' law for electric fields, where the integral of the electric field over the area of the surface, which is equals to the enclosed charge divided by the permittivity of free space. Second is the corresponding formula for magnetic fields. The integral of the magnetic field over the area of the surface equals to 0. Third is Faraday's law of magnetic induction. The integral of the electric field over the infinitesimal element of closed loop is equals to negative charge in magnetic flux divided by change in time. And the fourth is Ampere's law plus Maxwell's displacement current. The integral of magnetic field over the infinitesimal element of closed loop, which is equals to permeability of free space multiplied to current plus displacement current. From there, a series of simple algebraic manipulations extracted the wave equation from Maxwell's equations, which implied the existence of electromagnetic waves. Electromagnetic waves traveled with the speed of light, and life itself is an electromagnetic wave. And violin strings can vibrate at many frequencies, and according to the wave equation, so can electromagnetic. Violin strings can vibrate at many different frequencies, producing different sounds, as visible electromagnetic waves with different frequencies produce different colors. So, how about the applications of these equations in physical world? We have Heinrich Hertz, who was a German physicist that during 1886 generated electromagnetic waves at the frequency that we now call radio and detected them experimentally. And second is Guglielmo Marconi, who on 1895 successfully carried out the first wireless telegraphy and transmitted and received the first transatlantic radio signals in 1901. So in conclusion, this is just a sketch of an interaction between mathematics, physics, engineering, and finance where everything is complex and lengthy. This proves that mathematical discovery generally proceeds from the simple to the complex. No one knows where to start. Even violins are accidents of European culture. Remember, mathematics reveals the simplicities of nature and permits us to generalize from simple examples to the complexities of the real world. So, the next time you switch on your TV or watch a videotape, remember that without mathematicians, none of these marvels would ever have been invented.